In this session, we are going to talk about the martingales and measures, wherein the key topics that we are going to look at will try to define what do we mean by market price of risk, right? How do we define it in terms of the mean, the risk-free rate of return, and the standard deviation. Then we will talk about extending this market price of risk for several variables instead of one single variable. We'll introduce the concept of martingale, which forms a very essential aspect in the pricing of various derivatives, in the valuation of various derivatives. Then, under this understanding of martingale, we will move on to understanding the Black's model again for pricing the options, especially where the interest rate is not fixed, it is stochastic. The typical Black-Scholes model is trying to address the pricing of the option where R is assumed to be constant. Whereas this revised Black's model tries to look at the stochastic behavior. And towards the end, we will see one more application of this Black's model on the similar lines where we are talking of exchanging one asset for the other. If you remember, we have used that as an exchange option where I exchange one option, one asset for the other. How do I get into the pricing of those exchange options using the same concept? This understanding of both the martingales as well as the measures is very essential as a part of the risk neutral valuation process. And just as a definition, martingale is nothing but it's a zero drift stochastic process. Means probably when I'm talking about a change, it is only based on the standard deviation times the Brownian motion, Wiener process. There is no drift term that is present in it at all. So those kind of processes are typically called as martingales. And when we are talking about measure, we are strictly talking in terms of the unit in which we are valuing the security prices. Sometimes we may measure them directly in terms of dollar, or sometimes we may measure them in terms of another asset, some percentage of some other asset. Then that is what we are calling as measure in terms of what we are trying to value the asset prices, security prices. That is what we are calling as a measure. And we will be talking about what is called as an equivalent martingale measure. It's like this. If we use the price of a traded security, some G, the price of that particular security as a unit of measurement, means I will express the security X price in terms of the security's Y's price, which is G. If I say G is the price of the security Y, I'm trying to price the traded security Y. I use this price of this traded security Y, which is G, as a unit of measurement. Then what we are saying is there is a market price of risk for which all security prices follow a martingales. That's an interesting equivalent martingale measure result, which we will get a much more understanding once we understand all these definitions in a much more effective manner. So getting into that, first let's try to understand the market price for risk. So let's start off with the simple stuff. Property of the derivatives, all the properties of the derivatives, let's say they are dependent on one single variable theta. Whatever is the change in the value of that particular derivative, let's assume that it is depending on one single variable theta. And that theta, let's say it follows this kind of a relation. So there is some amount of MDT, which is the drift, and SDZ, which is working out to be the volatility aspect. So we are talking of expected growth rate in theta. At the its theta is growing on an average at the rate of m, and the volatility of theta is coming out in terms of s. Now, what I want to do is two different derivatives, f1 and f2, which both of them depend purely on theta. Right? A derivative is nothing but the ones whose price depends on the underlying. So I am saying there are two derivatives, f1 and f2, and the prices of them are purely dependent on theta and t. So because of that, what happens, I can very well write both the derivatives in this form. df1 by f1 is mu1 dt plus sigma 1 dz. Similarly, df2 by f2 as well. And probably in the discrete form, if I have to write, delta f1 is nothing but mu1 times f1 times delta t sigma 1 times f1 times delta z. The same logic goes with delta f2. Now, I am trying to eliminate the delta z term here. So how can I eliminate? I'll form a riskless portfolio. I'll invest how much? Sigma 2 f2, right? I'll put sigma 2 f2 times in this, and let's say minus sigma 1 f1 times minus sigma 1 f1 units of this. So obviously right now I'm having a portfolio where I'm taking delta sigma 2 f2 times, I'm investing in f1 security, and I'm taking an opposite position sigma 1 f1 times in f2. So my value of the portfolio right now is going to be this much. Sigma 2 f2 f1 minus sigma 1 f1 f2 is what is the value of my portfolio. And same way I can talk about the change in the value of the portfolio, which is delta phi. So I'll get it through this delta here. So sigma 2 f2 delta f1 minus sigma 1 f1 delta f2. So let me substitute what happens. Sigma 2 f2 delta f1 is mu1 f1 delta t, and now I know these two anyhow will go off, so I'll not bother about the delta z term, because intentionally we are making it delta z to be 0 itself. So I'll make it delta 1 sigma 1 f1 mu 2 f2 delta t. So this is what is the delta pi, right? So finally it works out to mu 1, right? Delta phi works out to mu 1 sigma 2 f1 f2 delta t minus mu 2 sigma 1 f1 f2 delta t. So this is what is coming out to be the change in the value of the portfolio delta phi. But if we see, when there is no delta z term at all, right, when there is no delta z term, we know that it's a risk-free kind of a portfolio, and there is no volatility. So it's a risk-free portfolio. If it is a risk-free portfolio, obviously the return that it has to give is r phi delta t. So this should be equal to r phi delta t. So I am taking this off. So finally, if I am taking it out, delta pi is r phi delta t, and probably here, if I am taking out mu 1 sigma 2, now if you are looking at this, mu 1 sigma 2 minus mu 2 sigma 1 f1 f2 is equal to r phi. And probably if you are looking at substituting pi, it is nothing but this is pi, So I can write it as sigma 2 minus sigma 1 times F1 F2. So I'll take this out. So finally it comes mu 1 sigma 2, mu 1 sigma 2 minus mu 2 sigma 1 is equal to R times sigma 2 minus sigma 1. Or probably do a kind of a small rearrangement. Right, I can do a kind of rearrangement here. Uh, Sigma 2 times mu 1 minus R is equal to sigma 1 times mu 2 minus R, and the other way is mu 1 minus R by sigma 1 equal to mu 2 minus R by sigma 2. This is what is the relationship that I am getting, and this is what I am calling it as lambda, which is what we are calling as the market price of risk. So whatever is the mean return of that particular derivative minus the risk-free rate divided by the volatility, that should be constant for all the derivatives which are dependent on just theta and t. That is what is the meaning of the market price for risk. So can be dependent on both theta and t, but it is not dependent on the nature of derivative. Whatever is the kind of a derivative, I'll end up with the market price of risk, which is nothing but mu 1 minus R by sigma 1. So for no arbitrage, this must at any given time be the same for all derivatives that depend only on theta and t. That's a very interesting result. So if I look at this numerical, consider a derivative whose price is positively related to the price of the oil and depends on no other. So it depends only on the price of oil and depends on no other stochastic variable. Suppose it provides an expected return of 12%, volatility of 20%. Assume the risk-free rate is 8%, find the market price of risk. 12 minus 8 divided by 20. So it's around 0.2. Consider two securities, both of which are positively dependent on the 90-day interest rate. So both of them are dependent only on this theta. Suppose the first one has an expected return of 3% per annum and a volatility of 20% per annum. Second one has a volatility of 30% per annum. Assume that the instantaneous risk-free rate is 6%, find the expected return. So we know both of them are dependent on only one underlying. So obviously their market price of risk should be the same. So I'll compute the market price of risk for the first one, which is 3 minus 6 by 20, which works out to minus 3 by 20. Same logic if I put here for this also, so whatever is the mu 2 minus 6 by 30, this should be equal to minus 3 by 20, right? So minus 9 equal to 2 mu 2 minus 12. So mu 2 is going to come out to 1.5%. So the expected return for the second one, we can very well work it out using this market price risk, because both the derivatives should have the same market price for risk. That's the typical way we define this market price for risk. Now traditionally, if I take it to the risk neutral world, right, wherever we talked about see, initially we said the price of the derivative df by f, we said it is mu dt plus sigma dz. Now when I am taking it into a risk neutral world, this mu will be equal to r. So that's the reason I get the derivative, the change in the price of the derivative is coming out to rf dt plus sigma f dz. So there the market price of risk is 0. When you are going into the risk neutral world, there is no risk at all, and when mu is equal to r, mu minus r by sigma is 0. So the market price of risk will be 0 in a traditional risk neutral world. And in general, when you are saying lambda is equal to mu minus r by sigma, I am getting mu equal to r plus lambda sigma, right? And we are saying df is equal to mu f dt plus sigma f dz. Now instead of mu, I'll write it as r plus lambda sigma f dt plus sigma f dz. So market price of risk of a variable determine the growth rates of all the securities. So I just need to find out that market, based on that market price per risk, I should be able to find out what should be the mu for all the securities that are dependent on that particular variable. And that is where the Gersonov's theorem also come into picture. As we move from one market price of risk to another, so if my lambda is changing from lambda to lambda 1, I am changing from one market price of risk to another. It's only the expected growth rates that are changing, but the volatility is remaining constant. Right? Even if the market price of the risk is changing, as long as anything else is not changing, only if the market price of the risk is changing, what we see is it is impacting the price of the expected growth rate of that particular securities price, but the volatility is going to remain constant. So choosing a particular market price of risk, how much do I really want? What is the market price of risk for this particular security is more or less equivalent to calling it as choosing the probability measure. So sometimes we are looking at it from the real world. Market price of risk, whatever we are talking, it's corresponding to the real world, and the growth rates of the securities are those that are observed in the real world in the practical space. The same concept of market price of risk, I can extend it even to several state variables, not just depending on one. Like look at a stock price depends on the price of the oil, price of gold, performance of a stock index, all three of them. Suppose the market prices of risk for each one are this much. So which means lambda 1, lambda 2, lambda 3 are known. Right? So three different market prices of risk are there. Suppose that the sigma corresponding to three variables. So I have the sigma I. So this is this. Sigma 2 is 0.1 and sigma 3 is 0.15. Now all I require is excess return over the risk-free rate. Right? We know mu is nothing but R plus sigma lambda. Now probably mu1 equal to R plus sigma lambda 1, that kind of stuff. Now when I am doing this for all, it's just as simple. Now R is something that I am, so it becomes mu is sigma 1 lambda 1 plus sigma 2 lambda 2. Even if there are multiple variables, it becomes exactly like this. So it becomes 0.2 times, so R plus this much, 0.2 times 0.05 plus minus 0.1 times 0.1 plus 0.4 times 0.15. Right, so this becomes minus 0.0 plus 0.01 minus 0.01 plus 0.06. So it's around 6% is the excess return of the stock over the risk-free rate. So even if I have several state variables to talk of, as long as their market price for risk as well as the standard deviations are given, I can very well find out how much in excess of the risk-free rate they are typically generating. Now, let's move to the the next important concept in this session, martingale. As a definition, we defined it even earlier. It's a zero drift stochastic process. So basically it is like when I'm taking d theta, I will not have, or d theta by theta, whatever it is, I will not have this mu dt term, right? This will be 0. So only this much will be present for a martingale. This is the form of a martingale. So expected value at any future time is, so the expected value, because mu is not changing, there is no growth rate. So the expected value even at a future date is equal to the current value itself. That's the important conclusion that is associated with a martingale. Whenever we are using the word martingale, the expected value at a future time is equal to the current value itself. So in this context, I want to talk about the equivalent martingale measure result. So for that, let's take a scenario. Imagine F and G are the prices of the traded securities. Two different securities, F and G, are the prices. So let me take securities X and Y. The price of X is F, the price of Y is G. And both of them are dependent on the single source of uncertainty, theta only. Just like in the earlier example, I have taken F1 and F2 are the two derivatives which are dependent on the single source of uncertainty, theta. So that single source of uncertainty could be a kind of an interest rate, and I can have two derivatives which are purely dependent on one single interest rate itself. Okay, assume that the security provides no income during the time period under consideration. So no coupons if it is a bond, or no dividends in case of an equity. Now this is where I am bringing out one representation called phi, which is just the ratio of the two prices F by G. So probably it says this is the price of forward and this could be the price of the option underlying the same derivative, underlying the same security. Now phi is what I am saying, the price of this forward contract divided by the price of this option, or in any way I can even talk about this is option 1, this is option 2, doesn't matter. Both of them are depending on one single underlying itself. The price of F in units of G but not in dollars. In that case, G is actually called as a numeraire. Numeraire is something whose price is taken as a base to express the price of some other security. And what we say is, when there are no arbitrage opportunities, phi is a martingale. Means the ratio of this, whether it is now or at a future point in time, the expected value of this ratio should be constant. Right? Otherwise, an arbitrage opportunity. So if today, if the price of F is 20 and G is 30, in the future, let's say if the price is if the price of the F goes to 30, it says the price of the G has to reflect the same ratio approximately. So it should be in that 2 by 3 format itself. So this may have to go up to 45. The ratio of 2 by 3 may have to be maintained. And that is where we are saying phi is a martingale for some choice of market price of risk. So for a given numeraire, that is where the importance comes. For a given numeraire, security G, the same choice of market price of risk, so whatever I am choosing as the market price of risk, makes phi a martingale for all the securities. So that particular market price for risk that I am choosing is what is making the phi a martingale for all securities of F. So when the market price of risk is set equal to the volatility G, the ratio is a martingale. So that is actually working out to be the volatility. So wherever I am setting the market price of risk equal to the volatility of the G, then the ratio F by G is a martingale for all the security prices F. So if I have to set the market price equal to the volatility of G, we can even look at that. Okay, let's look at the proof for the same. In general, okay, in general, I know mu is R plus lambda sigma. Now let me do it for, now we are making that lambda, which is the market price of risk, we are making it equal to the volatility of the G. So I'll find out that df is, how much is df now? It is mu r plus lambda, I'll take it as sigma g. So df is going to come out for us as mu f dt plus sigma f dz. The same I am taking, mu r plus lambda sigma times f dt plus sigma f dz. Similarly, dg, I'll get it as r plus sigma g f dt or g dt plus sigma g dz. Now I'll apply the Ito's lemma and go with d log f. So for log f, I'll get it as mu minus sigma squared by 2 dt plus sigma dz. Right? The same logic I'll bring in here. R plus sigma g sigma f minus sigma f squared dt, right, minus half sigma f squared, right? So I'll, because I am taking half dou squared f by dou x squared. Okay, so half dou squared dou f half sigma f squared dt plus sigma f dz. Similarly, I can take for d log g r plus sigma g squared minus half sigma g squared dt plus sigma g dz. So this is what I am getting. So from here I can say d log f minus log g comes out to this much. So it works out to sigma g sigma f minus half sigma f squared plus half sigma g squared dt plus sigma f minus sigma g dz. So d log f by g comes out to, probably if I am looking at this part, it is working out to, if I am taking out half outside, alright, so okay, this also, so if I am taking minus half outside, it is becoming sigma f squared minus sigma plus sigma g squared minus 2 sigma g sigma f dt plus sigma f minus sigma g dz. Now this comes out to half times sigma f minus sigma g whole square dt plus sigma f minus sigma g dz. And now again we can use the Ito's lemma to actually go back to this. So obviously I'll have again, if I'm going back, I may have to take out that minus sigma squared by 2 terms. So this term is going to go back, right? Minus sigma squared by 2 term, this part has to be taken out. So from the dt, if I am taking out this term, it's actually becoming 0 dt plus sigma f minus sigma g dz. So this is nothing but it's a martingale. So the df by g is actually becoming a martingale because there is no drift part of it in this. So what we can say is, if the market price for risk is set to the volatility, we can very well say that the f by g is following a kind of a martingale. That is what we are bringing out even in this result out here. Then, using all these stuff, there is an important thing that we can bring out as one of the interesting outcomes of this session. We know that the regular Black-Scholes-Merton model can be used to typically price the options where R is constant. But if that R is stochastic, this Black's model can, using the same concept of martingales and the change of the base, which is the numerators, it has finally come out. See, in regular thing, we say that the price of the call option is S naught ND1 minus KE per minus RT ND2. Now, in this model, what is going out is you go to the forward. So, under the assumption that you are changing, forward is nothing but S naught E per RT, we are shifting our base with this kind of a stuff. So, it's as good as instead of S naught, we are writing as F naught E per minus RT ND1 minus KE per minus RT ND2. So it's actually coming out as E per minus RT F naught ND1 minus K ND2. This is what, so the P0T is nothing but the present value, which is working out as the discounting factor E per minus RT. Now the same logic if I go with D1, so which means instead of S naught, I am changing the base to F naught. Now similarly we had D1 computation. D1 we had earlier log S by K plus R plus sigma squared by 2 times P divided by sigma root P. Now S I'll write it as F naught E power minus RT by K plus R plus sigma squared by 2 times T divided by sigma root T. Now this is actually log F naught by K log E power minus RT, log and E power, which is minus RT plus sigma squared by 2 times T by sigma root T. So the D1 is coming out to this much. D2 will still come out to D1 minus sigma root T. The same thing happens with the price of the put. Now what are we doing here? The S naught we are writing in terms of F naught. Again the change of the G itself, change of a numerator itself. And because both of them, S naught and F naught purely depends on the price of the derivative S naught itself, on the price of the original security S naught itself. So that's the way I can very well use it as a kind of alternative. So it implies both to investment and consumption assets, and it's true where the interest rates are stochastic, provided that F naught is the forward price of the asset. As long as F naught is the forward price of the asset, I can very well go ahead in terms of finding out the price of the call option even when the interest rates are stochastic as such. The same way, this simple example can very well be used to exchange one asset for the other also using the same. Probably if you are looking at V naught. Now let's say I am talking about an exchange option, exchange U for V. So U and V are two different assets. So let's say the current price of U is U naught and that of V is V naught. And we wanted to exchange U naught for V naught. So this is where again the same logic, because V naught I can very well write it in terms of U naught and the expected value of Vt by Ut. So I am expressing Vt in terms of the Ut price. And we know that this should be a kind of a martingale for us. So I'm directly, now that I know that U by V is what is the ratio that I am getting in, and I know that if one is expressed in terms of the other and no arbitrage opportunities are there, the ratio should be a kind of a martingale. So I'm saying here log, the same logic, log S by X. So here it becomes V naught by U naught. And I'm having that instead of R, I'll take the difference between the interest rates of both the securities, sigma squared by 2 times T, this much. So V naught ND1 minus U naught ND2 is what is going to be the value of that particular option, which is our value of that particular deal where I am exchanging one as a value of one asset for the other. And here obviously whatever is the sigma that I am looking at, it is the combined standard deviation, which will work out. The sigma has to come out as square root of sigma u squared plus sigma v squared minus 2 sigma 2 correlation between the two sigma u sigma v. So this should be the kind of standard deviation that should come between the two, and I can apply that and finally get into the problem of what should be the price of this kind of a option kind of a security. So again the same logic. I am assuming that U naught by V naught, or U by V, which is the ratio of those two asset prices which are behaving, going to depend on the same underlying, is again a martingale. So that's how we have tried to understand the concept of martingale in this chapter. We looked at the basic understanding of market price for risk. How does the market price for risk remain the constant for all the securities which are changing based on the same underlying variable? How the market price of risk remains to be the constant, even if there are multiple state variables. How do I look at the excess of return over the risk-free rate that should come for them using the market price for risk? Talked about the martingales, the basic definition of them, and the application of the martingales, where we have looked at the revising of the Black's model for finding out even if the interest rates are stochastic, and similarly the same concept being applied for finding the price of an exchange option also. Right? Thank you very much.